subject of this episode will be exact differential equations, and one motivation for studying those now is that these can be nonlinear differential equations. So here we have a nonlinear ordinary differential equation that is yet well understood and for which we do have a strategy to solve them. So that will enable us later to compare experience that we will gain now with a nonlinear type of ordinary differential equations with the experience that we had earlier with linear ones. Now that comparison linear-nonlinear is important, and so we will be able to do that based on what we learn in this episode, but I will make the comparison in a later separate episode. Also, exact differential equations that we will study now have applications in fluid dynamics. They have to do with streamlines, stream functions and gradient fields. Now those are important and related concepts in fluid dynamics. One remark: the perspective that you get on these type of concepts in a course like this, and especially in a textbook that we use, is you start here from the differential equation and we kind of come up with a solution, with a strategy to solve the differential equation, and ingredients like stream function, streamlined gradient fields are ingredients of our solution strategy. In real life application, if you work with fluid dynamics, you meet the same ingredients and they are related as they are related in this work that we will study now, but the perspective may be very different. The starting point might then not be the differential equation, but you might just know about the stream function somehow, or the streamlines, and then the differential equation that describes the mathematics of the streamlines is just one of the ingredients that you have in your toolbox to understand the situation. So keep that in mind. If at the end of this episode we mention some details of the application, keep in mind that in real life your starting point is not always the differential equation. So it is in that sense, for real life application, it is more important to understand all the ingredients and how they relate and be able to look at that from different perspectives, which is exactly what we do mentioning that application. But for now we just follow the textbook. So we start with exact differential equations. So let's go for it.
We shall study a class of equations known as exact equations. These are first-order, ordinary differential equations, but they may be nonlinear. Therefore, they may give us a glimpse of what nonlinearity may bring. We shall also have a look at a slightly more general class of equations that we shall call pseudo-exact equations. These are equations that can be reduced to exact equations by means of integrating factors. Exact equations also have a straightforward interpretation and application in fluid dynamics, and so they are of direct relevance to aerospace engineering. Consider a piece of a curve in the xy plane. Let this piece be the graph of a function y of x. Let y0 be the value of y for x equal to x0. Then the vector v with components 1 and y prime, and which originates from the point x0, y0, is tangent to this curve at the point x0, y0. If there would furthermore be given a vector chi, such that the inner product of chi and v would be 0, then chi and v would be perpendicular. Now imagine, vice versa, that we would specify vector chi and that we would do so at each point in a region in the xy plane. Indeed, let the components of chi be continuously differentiable functions m and n, of x and y. Then the combination of equations 1 and 2 can be written as the following equation, equation 3. Equation 3 can then be interpreted as an equation for pieces of curves. Each piece is described by a graph of a function y of x. The pieces are such that their tangent vector is perpendicular to the given vector field chi, at each point xy. A differential equation such as equation 3 is called exact if the vector field chi is conservative. That is, if there exists a scalar field, say psi, such that the vector field chi is the gradient of psi. Combining equations 3 and 4 gives To interpret this equation, interpret the pair x paired with y of x as a parametric description of a curve in the xy plane. X is the x-coordinate, but at the same time it takes the role of a parameter of the curve. Then equation 5 simply says that the value of psi does not vary along such curves. In other words, the curves that are locally described by the function y of x are level curves of the scalar field psi. The solution of exact differential equations can therefore be given in implicit form as psi of x and y equals c, in which c is an arbitrary constant of integration. In summary, we picture the situation as follows. We are given a vector field chi in the xy plane. The components of these are the functions m and n, both functions of x and y. M and n also appear in differential equation 3. This differential equation is called exact if and only if the vector field chi is conservative. If and only if that is so, the vector field chi is the gradient field of some scalar field psi. The values of this scalar field psi, in the xy plane, are depicted in the graphics by colors. Solutions y of x, of differential equation 3, correspond to level curves of this scalar field psi. Therefore, to solve equation 3, provided this equation is exact, we would go after this function psi. Now that we start to see a strategy to go for solutions of exact equations, we need a criterion to decide whether or not an equation of the form of equation 3 is exact. This is equivalent to deciding whether or not the vector field chi is conservative. You may remember from introductory courses in calculus that if a vector field is conservative, then its curl will vanish identically, provided the functions m and n have continuous partial derivatives. The left-hand side of equation 7 corresponds to the curl of the field chi in 2 dimensions. Equation 7 is commonly paraphrased as saying that the field chi is irrotational, or curl-free. From a course on calculus you may remember that, on an open, simply connected region, relation 7 provides a sufficient condition for a scalar field psi to exist, such that the vector field chi is the gradient of it. Hence, we can state that the differential equation 3 is exact if and only if the vector field chi is irrotational. in the two-dimensional sense. This provides us with a strategy to attack differential equations of the form of equation 3, as follows. First, we check if the field chi is irrotational. Then, second, in case chi is irrotational, we construct psi by integrating the two differential equations that are specified by equation 4, as chi is actually given. These equations are given here as equations 8. They are in principle straightforward to solve. In the first equation, the partial derivative is with respect to x, so y is to be considered a constant. Solving this equation therefore comes down to finding a primitive function of m, with respect to x. Note that this primitive may involve an arbitrary function that still depends on y. That function may then be chosen such that the second equation of equations 8 is also satisfied. The condition for this to be possible is precisely the condition that equation 3 is exact. You may also start from the second equation of equations 8, and work in the other direction. Finally, the general solution of the exact differential equation can be written down in implicit form. The form of this is given by equation 6. Note that the general solution contains precisely one constant of integration. If, in step 2, it turns out that the vector field chi is not irrotational, then we may bring in the strategy of looking for an integrating factor. Now, multiplication of the whole equation 3, by a factor mu of x and y, is equivalent to multiplying the vector field chi by a scalar field mu of x and y. We may do so in the hope that mu can be designed such that the modified field, mu times chi, will be irrotational. That is, we can substitute mu times chi for chi in equation 7, to arrive at, and take this as a condition on mu. That is, for mu to be an integrating factor for equation 3. In practice, when mu would really need to depend on both x and y, condition 9 is commonly as hard to solve as the original equation 3. Therefore, the approach of integrating factor does not actually provide a real, general, effective method for differential equations of type 3. However, if an integrating factor happens to exist that depends exclusively on x, or exclusively on y, then condition 9 reduces to a linear, separable differential equation for mu, and that can be solved. This route can be easily explored, so it is worth trying. In academic exam settings, the form of mu is typically given as a hint, to save some time in the exam situation. So it would, for example, be given that an integrating factor exists that depends on x only. As an important application of exact and pseudo-exact equations, we mention fluid dynamics. In that context, our scalar field psi here corresponds to what is known as the stream function. The vectorial velocity field of the fluid is then given by the partial derivatives of psi, by the following expression. This velocity field is obviously perpendicular to the gradient of psi, and so the velocity is tangent to level curves of psi. The level curves of psi are called streamlines. In that context, they are the curves along which the fluid flows. So, differential equation 3 is slightly more general, but, if it is exact, It corresponds to an equation for the streamlines of a stream function in fluid and aerodynamics. Then, the pair x paired with y of x, in which y of x is a solution of equation 3, is nothing else than a parametric expression for a streamline, with x as a parameter.